So today we are taking a closer look at radioactive decay. Now, say we have a radioactive isotope of uranium 238 and we have a sample that contains 16 nuclides. So 16 say atoms which have 16 nuclides of uranium 238. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and we can put one here, 16. So this is our sample. Uranium 238 has a half-life of 4.5 billion years. Now, half-life is the time it takes for a sample of radioactive element to decrease by half of its original amount. So half of this sample should decay to form daughter elements and give off some radiation. So let's go after 4.5 billion years. 8 of this 16 will randomly. So let's try to make this random. Half of the 16, which is 8, will decay. I believe this is 8. 1, yes, 8. So this is the first half-life. After the first half-life, half of the 16 is gone. So we can put a little label here, first half-life. No, our second half-life will be our second 4.5 billion years. So this is basically 9 billion years. In 9 billion years, we would have the next half-life. So in the next half-life, you would expect that this 8 would then decay. But no, it is half of what we currently have that will actually decay in the second half-life. So if after the first half-life we were left with 8 nuclides, it will take 4.5 billion years for half of that 8 to actually decay. So instead of all 8, only half of the 8 will decay, which means 4 will randomly decay after the second half-life. Now, this will continue if we should have a third half-life, 4.5 billion years again. And I believe we are somewhere around 13.5 billion years by now. Half of this 4, which is 2, will randomly decay. And this will continue until we have no more of the radioactive substance. We can actually graph this, and I went ahead and I graphed it. So we are graphing the amount of radioactive substance that we have versus the number of half-lives. So let's make n naught be the number of radioactive substance we started with, and let's make this 64. Let n be the number of substance we have after, say, each half-life. So n can be any number of substance remaining. So here I have 64. Let's use uranium 238. So somewhere around here we would have our n naught. So this is n naught or n0, 64. After the first half-life, we would have something like 32. So half of 64, 32. Somewhere around here, 32. So that's the first 4.5 billion years. Now after the second half-life, we're going to have 16. After the third half-life, we're going to have 8. Fourth half-life, 4. Fifth half-life, 2. But what happens when graphing this information, amount of substance remaining against the half-life? This graph will tend to 0, but it will never reach 0. But realistically, at some point we are going to have 0. But what happens is that the activity will decrease so much that it will take a longer time to reach 0. Also, this graph, this graph is an exponential graph, so it will tend to 0. It will not reach 0. It will tend to 0. Now, a formula we can use to actually determine the amount of substance we have remaining is N, any amount of substance, is equal to N naught, the original amount that we have, times E, natural, times E to the negative lambda. Now, lambda is the decay constant, T. And I will write those down for you.